Okay, student group in the front. Let's do a little exercise just to see how I am going. So this is like, when you go to a restaurant, they give you a feedback form. So this is my feedback form. Say something, just briefly, each of you. I'm going to start with the guy who just drank water. Red t-shirt. You, that's right. What did you think about what we talked about last? You're not there. Okay, you're excused. Next person. What did you take away? What did you learn?
It was enlightened, like what you spoke about. I've never known this before. So what you spoke about was interesting to know. Though it was a little out of context for me, first I couldn't understand it. But then as you went along, I left also early last time. But as you went along, I kind of got something. I understood about the data mining and things like that. Artificial intelligence that you spoke about, the debates that you all had. Pretty, I understood well.
Yes.
I just understood about the services modeling. So how a company can outsource different services from different companies, so that they can't have their own employees, they can only outsource. So this can make their work easy.
Okay. You think about some stuff, okay?
The same thing as you said, we can use the resources from outside, we don't need to buy them or earn them, and we can use the outside resources.
I wasn't there last time.
You were there?
So I learned regarding the outsourcing and plus the clinical or whatever you spoke regarding medical this thing. Also understood.
Okay.
So not there last time.
Not there?
I understood about the clinical part, about the oncology regarding that cancer thing, and also about the outsourcing the projects.
Outsourcing bit was a hot seller, right? Everybody picked up on the outsourcing. That's interesting. Okay.
So same outsourcing and clinical related things.
So outsourcing artificial intelligence.
Okay, the next person can't say outsourcing.
Data mining.
Guy in the black t-shirt.
So scope of research in this.
You took away the idea that there's interesting research.
So the scope for research.
And it's about AI and as you said about research, clinical aspect.
So I learned about the different ideas you can use, the computational service science like biomedical, then the data mining and stuff like that.
So I learned about the clinical thing, what you spoke about the medical wala, and the same thing clinical, and I understood that stuff.
I think we discussed a lot, so I'm pretty sure you took away quite a few things. So you're excused.
I understood about the starting. You explained about the computational science and service, two different concepts, and even the clinical part.
I like about outsourcing.
No kidding. I said that outsourcing was not allowed anymore. Something else, one other thing.
So you give the idea about that there are two medical experiments going on, with X people and X other people.
The clinical trials.
Yeah. I wondered why people why the people will go for X treatment even though they know that there is X plus Y.
So they don't know, right? They're randomly assigned.
Yeah, but then it's not ethical
Good. You took that point. Good.
The same thing what you said, artificial intelligence and the medical trials, how you spoke about the cancer and all, not just even if you have lung cancer, you can wait for radiation and all.
to show about the medical stuff and the AI. Then on the last thing here, it told about getting the results of the future thing, like the drugs and about Russia and all you told. You had said one that.
I said anything about Russia?
No, I think so. About in medical terms, some things you had said no at last.
Does anybody else remember Russia? That's an interesting one. I can't remember Russia. Okay.
Getting.
You were not there? Okay. You're excused. You asked a lot of questions. Okay, all right. I made a sale. I don't know what sale I made. I think I sold outsourcing somehow and some clinical stuff. Okay, that's something. That's better than nothing. All right, so let's start today's part of the story. So this is where we stopped, right? So I haven't gone through my first lecture's slides. So we're kind of doing the second half of the first lecture in some sense now. So one of the things I gave you all as a homework over the weekend is to go and quickly review this little bit of mathematics, right? This is the kind of mathematics that any computer scientist should be familiar with, because these are the tools of our trade. I mean, there are a few other things that we use, probability statistics, but they're not very important for this particular course. So I didn't mention those, but this bit, right? So hopefully you've looked at it, and I will at some point, maybe quite a bit later in this lecture, I'll start using it. And when I do, if I use notation that doesn't make sense to you, stop me and say what's going on, right? So feel free to stop me. But again, remember this, as a computer scientist, one of the best places to be in is to be the kind of person who is happy writing code, and I think you're all happy writing code, right? So you're all learning how to write code. If you can write code and you can do maths, then you're a very potent combination. And that's very rare to find across the world. There are coders and there are people who do maths. And the number of people who do maths is much smaller. Right? Most people are scared of maths. Fewer people are scared of coding, so a lot of people will code. But one of the saddest things in the reality we face, and this is not specific to India, it's international, is that far too many people run away from the maths. But maths is really, really important. It's really useful, and if you can get yourself to a point where you say, I'm not scared of maths, give me more maths, then you're in a really, really good place. Okay, so let's talk about some things. In fact, curiously, the thing that I'm going to talk about next has a little bit to do with this fear of maths, and I'll touch upon it. Okay, so we did the broad overview of computational service science on Saturday, and I know you took away bits and pieces of lesson, the story about data mining, about AI, about outsourcing, about clinical stuff, clinical trials and so on. But overarching picture, remember, is this. We are trying to marry computer science and management. We're saying that computational techniques can support all kinds of management tasks, right? So computational service science, so service is the metaphor, right? So of all economic transactions in society, in human society. And we're saying we're going to understand how services are done. In other words, we're going to understand how people do business, how companies do business, how they're managed by using computing techniques. So it's a funny mix of software engineering with applications in management and so on. So it's a bit like that. So think of it in those terms, right? Don't just take away outsourcing, clinical, data mining, AI. There's a lot more there, right, that we're talking about. Correct. So that's what we're saying, right? So the example I gave of servitization, right? The old model was I buy a TV. The new model is I pay for a service, where the service provider promises to keep a functioning TV of a certain specification in my living room for the service delivery period, right? So that's servitization. It's a very simple economic shift, right? But I mean, that is something that drove the thinking into service science and so on. So now we're going to go into modeling, and so I take it all of you are doing software engineering in some form or the other. You are, right? Yes? Software engineering, everybody? More or less? Somebody said no.
So what has happened is the course would have started by now, right? But very recent.
Okay, so it's just beginning to sink in. Okay. All right, so you will, then maybe it's a good thing to start with. So we're going to talk about modeling, right? And so a lot of software engineering is about software modeling. There are languages, modeling languages like UML and so on that you're going to learn in your software engineering classes. Here we are going to learn a different kind of modeling language. In particular, we'll look at a range of modeling languages. But to understand why we look at modeling languages and why it's important if you're doing software engineering, if you're doing many, many other things, let's look at the idea of modeling. To understand modeling, let's look at this picture. So what's happening here? Who's an aviation enthusiast who can tell me what's happening in this picture? Something that looks like an airplane, right? Good point. A wind tunnel. This is a wind tunnel, right? So what happens in a wind tunnel? Aircraft designers?
You check for the aerodynamics of the
Correct. So aircraft designers will take a scale model. The important word here is the model. That is a model, right? They take a scale model of an aircraft, park it inside these special devices called wind tunnels, where they can blow wind at various different speeds and turbulence and so on and so forth. And they basically want to answer the question, will the structure of this aircraft withstand various wind conditions? Sometimes you worry, right? If you're sitting in a plane and there's turbulence and you see the wing going up and down like that, you're saying, I hope they designed it correctly. I don't want the wing to break off, right? So they're structurally studying the design of the aircraft under various wind conditions. But the important thing here is that they're using a model, right? So it's a model. So what's a model here? It's an airplane, right? It looks like an airplane. It looks like a passenger airplane, or maybe a business jet or something, but still a passenger airplane with a fair few passengers that you can fit in. So if you look at one of these wind tunnel models, what you will see is that you will see the structure of the aircraft with the right materials and so on in the wind tunnel model. But you will not see, for example, chairs inside the plane, or the cockpit instruments, or the little TV sets at the back of a seat, or the food being cooked in the kitchen, the galley of the aircraft, or the coffee being served. You will not see any of that inside, right? We don't care to model that. We only care about the structure of the aircraft. That's very important, right? This is the basic idea of modeling. So modeling is used everywhere. And it is used as a means for abstracting the important things and throwing away the rest. So think of that as the very basic principle of modeling. And as computer scientists, we are all interested ultimately in building models. This is our stock in trade. This is exactly what we do. We build models and we analyze models. Now the models that we build can be of various kinds. You can build mathematical models. So if you're interested in this kind of spy fiction and so on, you will know that, across the world, countries that build serious weapons, sometimes nuclear weapons, missiles and so on, they find it very hard to test these things, right? So sometimes some country would go and test them and everybody else gets angry with them and so on, right? So what's the thing I can do if I want to build a complex weapon system, just as an example, without building it and blowing up a bomb or something? How do I test it? So one simple way of testing it is to build a mathematical model of it. So I build a mathematical model and I test the mathematical model. So what is a mathematical model there? It is a description of the behavior of that thing. In our example, it's a weapon system, but it could be many other things. It could be a spacecraft, it could be an aircraft, it could be a submarine, it could be anything. We build a mathematical model that describes the behavior of the thing we're talking about. But it's a model that can be executed, which is to say what is the execution of a mathematical model? If I have a model that has only one equation in it, x plus y equals 5, then the execution of this model is for me to say, let me set x to 2 and then find out from this mathematical model what is the value of y. And the mathematical model will tell me, well, if you set x to 2, y will be equal to 3, right? As one example. Y can take other values also? Yes. What's another value that y can take? If x is equal to 2, x plus y equals 5. Think hard. Okay, but you get the idea, right? So that's a mathematical model. Just an equation, one equation with two variables. And the act of executing the model is the act of saying, okay, what will happen to this system if I do this? So in this little example, if I do this means I set x to 2. And what will happen to the system is translated to a simpler question, which is what becomes the value of y? Right? So it's a pretty simple mathematical model, but real mathematical models get very, very complex. So, but it's a very powerful way in which you can test a system, the properties of a system, without building the system. So physical models, we just saw one, right? The physical model of an aircraft, an abstraction of a real aircraft. So I'm trying to figure out how the thing will behave without building the full aircraft. So I build the model, park it in a wind tunnel, and see what happens to it, right? So then there are other kinds of models. So a lot of people do agent-based modeling. So this is very interesting stuff. So a lot of my colleagues where I am located are agent-based modelers. They build complex models of very complex systems by defining the behavior of much smaller components. So one of the things they're doing, for example, is building a synthetic population of Australia. So Australia has about 23 million people. So a synthetic population of Australia consists of 23 million distinct software agents. The spread of behaviors across these agents represents the statistics that are collected via censuses and so on. Right? So, for example, if the census data says that 40% of all people in Australia own cars, then in the synthetic model, agent-based model of the nation, 40% of the agents will own cars, 20% will be smokers, 10% will take the bus to work, and so on and so forth. You take that, and then for a specific geography, like a specific region of a city, you can use that model to answer questions such as, if I lay a tram along this road, how many people will use it? How many less car users will we have? What will be the impact? And so on. So this is agent-based modeling. So we take large collections of little computational entities, each of which is an agent, and then we run the whole lot and say, okay, how does this thing work out? So it's a very interesting way of doing modeling of complex systems. So there's this much larger area called simulation, where you build models of various kinds, and you run these models essentially to answer the questions about how will this system behave if I do this, without actually having access to the system itself, without building it, without being able to test it, and so on. So if I said, if I lay a dedicated bus lane through the main streets of Panjim, right, and I want to answer the question, how many people will use it? At this point, it's a random guess, right? You take the population of Panjim, you think for a while, you say, okay, maybe this many tens of thousands of people will use it per day. But with the agent-based model or with simulation models, you can get much more precise answers. So this is modeling again, right? A lot of stuff that happens with modeling is also sometimes graphical. And when those of you who are doing software engineering, when you start looking at software engineering models, you will see a lot of graphical models, but you will see also a lot of what are called in computer science and software engineering conceptual models. So this is a very interesting thing. So keep in mind that some of the most popular software engineering modeling notations are conceptual modeling notations. So UML, for example, and so on. Right? These are all, or if any of you have done databases, entity relationship diagrams, right? These are all conceptual models. So what is a conceptual model? So a good colleague of mine, who is the most famous personality in this space, John Molopoulos, he defined it as knowledge representation for the purpose of building a shared understanding amongst stakeholders. So a lot of these kinds of models are, so it's interesting, they're not purely mathematical. So the first kind of model that I talked about is not particularly good for building a shared understanding. I mean, if you're doing a group project, you don't write a bunch of partial differential equations on a whiteboard and then stand around it and say, I think that one is wrong, and so on. You don't do that, right? Because it's very hard to understand what's happening with that partial differential equation. But if you draw a graphical model, you can kind of say, yeah, okay, that box and that arrow, it should go somewhere else. Right? So it's much easier to do. So conceptual modeling is what is used in software engineering. So I often teach a requirement specification class at the University of Wollongong. In my first lecture, I often say that, we're going to learn a lot of modeling notations here. But there's one interesting fact to keep in mind when you learn all these things. We use these notations because people are scared of maths. So there is this massive multi-trillion-dollar industry out there in conceptual modeling whose very reason for existence is the fact that people are scared of maths. Because if they were not, I would use mathematical models. They're much better. They're more precise, and so on and so forth. And if you're a really good mathematician, you can look at a bunch of equations, and internally you will know exactly what's going on with those equations, right? But people are not like that, right? People look at equations and then say, okay, I'm running for the hills, because I'm scared of this stuff, right? So you're scared, right? And so we have these conceptual models, and we'll see one now. And it's very interesting. There are many stories about how they get used and so on. So they're a mix of textual and graphical, and they have semi-formal semantics. Okay, I'm going to use the word semantics. How many of you know what that means? Semantics? One of you, okay. So semantics. So this takes us to language theory. So if you take any language, there are two parts of a language that are of interest: the syntax and the semantics. So all of you have done programming? All of you. Nobody here that's not done programming, right? Okay, good. So you know about the syntax, right? Whatever programming language you're using, it has a syntax, the rules of grammar. And your compiler or interpreter will check the syntax of what you write, and they'll give you syntax errors if you've written the wrong thing, etc., etc. There's syntax, the rules of grammar. And then there's semantics. So semantics is essentially a mathematical, but not always mathematical, most times a mathematical description of the meaning of what you've written. Right? So you can ask the question, okay, what is the meaning of this C++ program I just wrote? And trivially you will say, okay, so I wrote some lines of code, right? That's the meaning. I take X and I add 1 to it. I do this for loop. I do this sort of stuff. That's the meaning, right? But it's actually not. And why are we interested in the meaning? So we're interested in the meaning of programs, just as an example. We're interested in the semantics of programs because we want to be able to prove properties about these programs. So when I was at the University of Illinois at Urbana-Champaign, I had a fellow PhD student, an Indian guy, who was doing his PhD on programming language semantics. One of the funny things he used to say was, I can't wait for the day when there is a robot performing surgery and the robot botches the surgery, makes a mess of it. Because that is the day when people will take programming language semantics seriously. Which is to say that programming language semantics is about having the mathematical tools available to prove the correctness of programs. I write a program, this program is going to control a spaceship, an aircraft, or a robot that's performing surgery on human beings, and there are many such these days that are routinely used. You want to prove certain properties about the program, right? You want to say that I can 100% quality assure this program is never going to do the wrong thing, and only when I'm that sure will I actually use the program. Have all of you heard about the famous software disasters that happened because of divide by zero errors? Some of you have, right? So there was things like spacecraft that blew up on launch because of a divide by zero error. The cardinal sin for a newbie programmer, right? You write a divide by some value, and that value you permit it to get zero as a value. So divide by zero errors are dangerous things, right? So again, when we write our programs, we want to make sure that it does the right thing. To be able to do it, we offer semantics. Semantics is basically a mathematical mapping from things in the language constructs, to things that exist in the real world, but we don't actually have a real world. So it's like me saying, okay, I use the word laptop, and then I point to this thing and say, okay, this is what I mean. When I use that string of letters, LAPTOP, this is what I mean, right? So it's kind of that, except that I don't actually have access to the real world objects. I don't have the real world. I have mathematical representations of them. So I create a mathematical representation of the real world. I take the language and I map things in the language to the mathematical representations of real world things. So that's semantics. You can talk about the semantics of any language. So people work on the semantics of programming languages, mainly people who are interested in quality assuring your programs. But people also talk about the semantics of natural languages. So there are linguists around, and maybe there are some at Goa University, who are interested in the semantics of spoken language. Marathi, Konkani, German, Japanese, whatever, right? They have semantics. So people do it at all levels. So conceptual modeling languages are also languages, and even they have semantics. And these semantics can be very, very useful, and we'll see why in a second. So for these reasons, keep that word in mind, semantics, right? So you already know the word syntax. Now you're familiar, hopefully, somewhat with the word semantics. So how does a model help? So we started out by saying that it's a means of abstraction, right? So you're abstracting away complexity. So the act of abstraction is the act of removing unimportant, irrelevant detail. Right? So in that airplane physical model in the wind tunnel, we didn't bother to build a model of all the seats inside the aircraft or the people sitting inside it and so on and so forth, right? Because we said that's not really important for the purposes of the analysis we want to do, right? So we throw away those details that are not important for the purposes of the analysis we want to do, and we keep only those details that are important, right? And that's abstraction. Think about it this way, computer science is all about abstraction. This is the one thing computer scientists are best at. We are good at building abstractions. And this is also very important, and mathematicians also realize this. Sometimes building the right abstraction for a problem suddenly solves the problem. I can think of a problem in a certain form and it's incredibly complicated. And it's not very easy to solve. But I suddenly think of it in a different form, I use different abstractions, and suddenly it's extremely easy to solve. When I was young, I read a book written by a man called James Watson. So James Watson and Francis Crick got a Nobel Prize for doing something very famous. Watson, Crick, anybody? DNA, that's right. The double helix model of the DNA, right? That's what they did. And you know what abstractions they used? For the molecule, the DNA molecule, they used ball and stick models. So the balls were atoms, sticks connected atoms, right? So H2O will have two little round balls that represent the two hydrogen atoms, and one ball representing the oxygen atom, and sticks showing the molecular connections between them. So they used a ball and stick model, and they played around with it. And you can, if you go on the web, you will see photos on Google Images of these two young people, black and white photos, pushing around these ball and stick models. And ultimately, by pushing these abstractions around, suddenly they came upon this very funny structure, the double helix, and they suddenly said, okay, this looks exactly right when I look at the X-ray crystallography pictures of DNA, right? And so they said, yes, this is it. This is the actual structure of the molecule. There is another very famous chemistry story some of you might remember from high school chemistry. Benzene, exactly. This guy called Kekulé, right, had a dream, kids holding hands, going around saying ringa ringa rosie or whatever, right? So that was the structure of the benzene molecule, right? Abstractions, the right abstractions suddenly offer solutions to hard problems.
So another interesting example I think is heliocentric theory and geocentric theory.
Yes, there too the models are very important, right?
Ptolemy's model was really complex when he gave the geocentric theory. Ptolemy gave the geocentric theory, the model was really thick. And for retrograde, he actually added concepts which were not in mathematics at that time.
That's right. So this is also interesting because when you abstract, you don't abstract by just saying, okay, I'll throw away unimportant detail. You're saying, I want to do certain kinds of analysis, and for that kind of analysis, I don't need this kind of detail. So let me get rid of it, right? So it's purposive abstraction. You have a purpose in mind, and you're abstracting, you're pulling out the important bits and throwing out unimportant detail, driven by what purpose you have. The purpose being the kinds of analysis you want to do, the kinds of stuff you want to do with the model. So ultimately it's about being able to say things about a system without having access to the system itself. So in software engineering, one of the classic experiments that are frequently quoted, there was an experiment done a long, long time back, I think it was the 70s or maybe late 60s, where they took a bunch of programming teams and they gave them the same assignment, same coding assignment. And it was done over a period of 8-9 hours, and they had a person tracking each team. And they saw how they went. And different teams performed differently on the coding competition, really. So they found that the best teams were those that spent time doing modeling. So there were some teams that said, okay, programming assignment, let's start writing code, zip, zip, zip. They were writing code. But there were other teams that said, no, 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 coding comes much later. Let's first do the modeling. Let's do the software modeling. Let's build the models. And then much later we'll write the code. And those teams did far better than the ones that just jumped straight into coding. Right? So there's value in modeling in standard software development. Right? Okay, so one of the interesting things is that we're also going to use models now in a very specific sense. We're going to look at a lot of behavioral models, models that describe the behavior of a certain system. And here the models are also, so we're not just really analyzing models, we are executing models. So we're sort of saying that whatever model we build is ultimately going to be the basis for the execution of my system's behavior, right, which is a really important thing. So there was a time when in software engineering it was really popular to build executable specifications. So a specification is a high-level abstraction. I'm going to build a million lines of code down there, but I've not written anything yet. I'm just building a specification, very high-level description of the future million lines of code. Right? That abstraction. So people were very interested in trying to figure out if there were languages where I could do that abstraction and I could execute that abstraction, run the abstractions. These were called executable specification languages. And curiously, the one language we will look at now, a modeling language for modeling services or processes, is in fact an executable specification language. You devise something that looks graphical and quite easy, and then you park it on a process engine and it runs. It's a program. It can be executed. So behavioral models are kind of important because they're the basis for execution. And so how complex that specification is, how flexible it is very, very important. And there's a really important philosophical insight here, which says that, the language we use determines the lens through which we see the world. If you're only allowed a binary language, you have a fixed set of bits and they can be given a value of 0 or 1. You can describe the world, you can look at the world through a very, very, very tiny lens. You can't say much about the world, right? You need more expressive languages to say things about the world. So they say that the German language has possibly the broadest range of words to describe different emotional states, right? So that's interesting, right? These guys could talk about subtle differences in emotional state because they had access to a vocabulary that allowed them to do that. Right? If you're a furniture seller and you have a very limited vocabulary and you say, okay, sir, what do you want to buy? I sell chairs. And you say, do you have a reclining chair? The guy said, I don't know what you mean by reclining chair. I only understand one word, chair. This guy's going to not do much business, right? Because I'm going to go and say, give me a reclining chair, give me an armchair, give me an office chair. And this guy doesn't know these distinctions. He only knows one word, chair. I sell chairs. So if you ask for a chair, I can give you a chair. You see, language is very important. The diversity of the concepts allows a diversity of behaviors. So this is something that to keep in mind in all of the things we're talking about. Okay, so now we're going to talk about some really interesting things that have to do with the real meat of what we're going to talk about. I'm just going to time myself here. So we're going to talk about service and process modeling. So what are processes? We're going to use this word a lot in the next few lectures. So good for you all to know what a process is. A process is a plan. A process is a coordination model. A coordination model is very interesting. One of the things that you will realize that a process description does is it coordinates activities, but it doesn't do the doing. It says, okay, you do this, and you do this, and after you've done that, you do this. So it's coordinating, it's the coordinator, it's giving the orders, it doesn't do the doing. It's a coordinator, it's a manager, it's a whoever, right? Some kind of a person that's, yeah, exactly. So it's a very interesting thing, and when we look at process models, you'll see how that works out. But it's, you're not doing, you're coordinating. And so a process model is a coordination model. It's not a pure execution model. But it's still a description of behavior. It's kind of like an algorithm. But the one difference between an algorithm and a process model is an algorithm actually does stuff. It changes the states of data objects. A process model in itself does not change the state. It assumes that there are execution machineries out there that it's coordinating that does the actual state changing. So doing is state changing, right? The act of doing something is the act of changing the state of something. The act of switching on the light is the act of changing the state of the light from off to on, right? So that's doing. But a process is also like a business strategy, therefore. First I'll do this, then I'll do that, then I'll do something else. So for example, this is a real example. I was reading on an in-flight magazine, a New Zealand company saying, we're a New Zealand company, and there's a very interesting joke about this. Many of you might not know this, but in Australia, sometimes, in a joking fashion, people tend to look down upon New Zealanders, who are called Kiwis, right? So a New Zealand company might have less credibility coming and doing business in Australia than if it were a UK company, who the Australians look up to. So if it's a UK company coming to do business in Australia, they have a lot of credibility. So the business strategy for this Kiwi company, this New Zealand company, was, first we will grow big in New Zealand. Then we will open up operations in the UK. And then we will use the UK operation to open an office in Australia. So now we are entering Australia not as a Kiwi company, but as a UK company. And that's just an example, but what is it saying? It's a sequence, it's a plan, right? First I'll do this, then I'll do that, then I'll do this. Right? Also a process, but it's a business strategy. So it's very interesting. Even business strategies are often processes. Right? So now there's this question of, we talked about services, right? So service is one piece of functionality that is outsourced. Right? Somebody does it service for me, and I consume the service. So in 2007 at the International Conference on Service-Oriented Computing, the Services Computing Conference in Hawaii, so I was asked to give a tutorial on service and process modeling. And a PhD student of mine and we were doing this tutorial. It was a 2-hour tutorial. But the funny thing was that there was a whole bunch of industry people in the audience. And the minute I started out by saying, people, I will use the word service and process interchangeably, which is what I want to do today. They all went haywire. The Boeing guy said, no, in Boeing, service is high level, a process sits underneath it. And the Microsoft guy says, no, in Microsoft, the process is a composition of services. And they went on for 45 minutes out of a 2-hour tutorial debating this, right? And I stood there and said, oh, okay, my tutorial isn't happening. Let them fight it out. What a service and process means. So they did, right? And so the reason I'm telling you the story is that you sometimes find that, but really it's not very important. You have to think of either a process as realizing a service. So the service is the outer packaging, the encapsulation of the process, the plan inside it. Or you can think of the process itself as being a composition of services, and we'll come back to that, but keep that picture in mind. So how might we specify a process? So let me jump to a picture of a process, which is an easy process. There's a process model, right? So there are those boxes which are tasks or activities, and they're connected by each other. And some of you are looking at this and saying, I think I saw this in my first year programming textbook. It was called a flowchart. Everybody seen a flowchart before? Right? Looks a lot like a flowchart, right? It more or less is a flowchart. That's it. So that's a process model. Now, interestingly, one of the funny things I will show you is that You might have quickly gone through the pages on flowcharting in your programming textbook and said, that's easy. There's actually incredible complexity inside a flowchart, because a flowchart is a very powerful device which can describe all kinds of very powerful things. So what does a flowchart tell you? It's a procedure, it's a recipe, it's a process, right? It says first receive open new account request, then you do a little test, and then you open an account, then you send a bank card and send a PIN, or you create an account and do a credit assessment, all kinds of stuff, right? So this is what the process is telling you to do. Right? So that's one way of thinking about a process. A process is a description of a sequence of things you do, plus some logic, some decision logic inside, right? So one of the decision logic points is right here, and we'll see that. That's a XOR gateway. Right? So this is a process. So processes are very useful devices for a lot of organizations. So you'll see many good hotels, they have process models like this for their check-in staff. So when the customer arrives at the check-in counter, first you ask the customer for their ID details, then you look up this, then you give them a welcome drink, then you do allocate a room to them, etc., etc. It's a standard process. There's one airline I fly a lot from in and out of Australia every year. That airline, I fly so frequently, it's almost like a second nature. I expect them to do this. I sit down, plane takes off. First thing they do is they come and give you a hot towel. So I wipe my face with a hot towel. Then they'll come and give me a menu card. So I look at it quickly and put it in the back of the front seat. Then they'll come and give me some juice and peanuts, and I eat the peanuts and drink my juice. Then they will come and give me my meal. After they give me my meal, they'll come with a trolley saying duty free. So it's like literally a standard process that's repeated over and over again. That's a process, and it's a very powerful device because, again, that airline uses a model like this to train its staff that, okay, people, this is how we're going to treat our customers on the plane. Exactly, the same thing. Yeah, I think Shatabdi Expresses do that kind of thing, right? Yeah. Yeah. I've only ever once been on a Shatabdi Express, having not used Indian Railways much in 28 years, but yeah. So that's something like that, right? So this repeatable procedures, that's a process. So given that, how might you model a process, right? So by specifying what must be done. What we looked at in that picture was exactly that. First you'll do this, then you'll do that, then you'll do that. The things we're talking about now. That's how a process is specified, by describing what is to be done. So you're sort of using procedure names, right? There is a procedure called give the passengers a hot towel. There is a procedure called give them a menu card. There's a procedure called give them a fruit juice to drink, and so on and so forth. Right? But this is somehow very limiting also, because you'll see in many other domains, that's not how people think. So if I'm a hotel check-in clerk, or if I am a cabin crew person on an aircraft, I might be following something like that. It might make sense to me. If I am a call center operator for an insurance company that takes insurance claims calls on the phone, I might follow a process. In fact, they actually do. Anybody been in a call center? No? Oh, you're missing a lot. Anyway, you'll talk to lots of people from Australia and the US if you're in a call center. But anyway, so they have these processes, these designs, like in the kind of notation I described to you. On their screens, they follow it step by step. This is the first thing, that's the second thing, and so on and so forth. So that's one way of doing it, but it can be very limiting. Now think about a doctor, right? So a doctor is preparing a patient for surgery. So a doctor won't say, okay, first I will give the patient this pill to reduce blood pressure. Then I will give the patient that pill to reduce blood sugar, right? And so on. They don't think like that. Instead they say, first I will lower the blood pressure. Then I will lower the blood sugar. Then I will send the patient to surgery. So what's the difference between the first style of thinking about a process and the second style? In the first style, I'm saying this is what is to be done. In the second style, I'm saying these are the effects I want to achieve. So I'm thinking in terms of effects. So what's the difference? If I say I want to lower blood pressure, that's an effect I want to achieve. But if I think in those terms, I'm allowing the possibility that I might use this pill or that drug, depending on the circumstances. What is really important is that I want to achieve the effect that the blood pressure is lowered. Right? So this is a big leap. Right? So you can think in terms of procedural terms and say, here's a task name, here's a procedure name, and you sequence them. Or you say, I want to achieve this outcome, then I want to achieve that outcome, and so on.
Other than clinical organizations, which organizations it would be better to actually in terms of exercise?
So any setting where you want to allow runtime flexibility, right? So we are the special forces planning a surgical strike. I don't know what I will face in terms of enemy resistance, right? But I have certain effects, certain goals in mind. First I want to take out this camp, then I want to capture these guys, then I want to get out of there safely and back to my own territory, right? This is more important than saying first you aim this weapon, then you shoot there, right? So the procedural detail is less important. The outcomes and which sequence you want to achieve these outcomes is far more important. So any setting where there is a need for allowing considerable runtime variability, and that also means autonomy, right? So this is common in military, right? So the senior officers set high-level goals. The more junior the officer is, the more lower level the goal they're using. And at the junior most level with the foot soldiers, the jawans and so on, then you are literally given low-level instructions. Aim your gun and shoot, or run there, or something of that sort, right? So this is common, right? So again, military is one example where there is a considerable need for flexibility.
So is it okay if I say that the lower the level is, the more procedural we want, and the higher the level is the... Exactly. Now let me give you other examples. So whenever one talks about military, right, one can also talk about business, because we know now there's a big literature that says business strategy is like military strategy. So businesses are the same thing, right? I want to first position my new mobile phone product in this market. That's a very high-level specification of the outcome you want to achieve. That's not a procedure. There is no procedure for positioning your mobile phone product in a certain market. There are thousands of different ways in which you can do it. I'm not even saying which way I want to. That I'm leaving to lower level people to decide on a context-driven basis, on a context-sensitive basis. Depending on what's going around, I'll pick the right procedure. Right? So business strategy is much the same, right? But even human thinking is much the same. Right? So there is this idea of human behavior being a mix of explicit deliberation versus the direct execution of compiled code. So if I, as a human being, happen to touch a hot object, right, the first thing I do is my hand jumps back. Am I thinking, planning on what to do? So am I saying, okay, my finger is touching a hot object. At this point, amongst the many courses of action, the best course of action is to gradually retract my finger. Do I do those things? No. I have a compiled program ready-made, right? It says, I touched a hot object, bang, it goes up. I don't even think about it. So it's pre-compiled. That program is pre-compiled. On the other hand, if I'm sitting and saying, okay, so today I've got to teach these guys at Goa University something interesting about process modeling and service modeling, how should I do it? There is no pre-compiled program that I say, okay, run that program and it will tell me how to do it. Now I have to think, I have to deliberate. So in human behavior also, there are certain things that are directly execution, that involve the direct execution of pre-compiled programs, and other things which involve the design of programs, right? So when this morning I was thinking about which slides should I use for the guys today, I was deliberating, I was designing the program, not directly executing a compiled program, right? Does that make sense to everyone?
Snacking too much of details at a higher level, not a higher level abstraction. Will it not lead to collapse of systems of other time? Because we're taking out only lower level of the details.
Yes, again. So you're saying abstraction of
Lower level, it's a lower level, higher level abstraction.
So you're saying, is it good to keep the high level abstractions the bare minimum?
Yeah.
We are losing the reality. That's what in general.
No, but sir, usually when you are writing any sort of, when you are planning any sort of study, at higher level you only talk about
what happens.
even our software architecture today is very dynamic. So when we are working with our Windows application, we are not worried about how the operating system is run.
So that's what happens. What happens is, take an army. Coup attempt happens. Thanks to have a lot of details to learn, high level abstraction. You are doing your lower level. High level abstraction hits everything on details. So that might lead to a situation like that. Coup attempt led by the army.
So, but you see, one of the famous phrases that military people use is that the best laid plans collapse in the face of the heat of battle. So you can plan your campaign in the last decade. Once you start the campaign, things happen and all the plans go down the drain, right? Because that's what happens. So then the abstraction comes in, because you need to know, okay, so my current attempt to capture that will fail. So, but I still want to capture that. So the effect I want to achieve still remains true. I want to achieve that effect.
Basically, abstraction allows flexibility.
Try in different ways.
What against it? The amount of details that we need. How much like as a patient, it's an interview model in abstraction. That's exactly correct. So we go things like scale chart, which can be planned as a model, programming model. We try to model which can capture some details.
So do these guys know state charts and very good. So think about what I talk about in the context of finance equations and state charts. That's a very interesting question. Did you ask your question?
Actually,
what you're saying that there is a need for there's a need for connecting the low level stuff to the high level abstraction. I think that is kind of like business activity monitoring. I'm sort of saying, okay, I want to translate what's happening down there to the high level abstractions and get a good assessment of how far we are. So I'm the colonel who's ordering the attack on the hill. So do I need to know that, okay, that gun is right now behind that boulder and we fired? No, that's unimportant detail. I want the detail abstract out by my major or captain reporting to be served. We are 20% up there. So for me that's important because I am dealing with that level of abstraction. The guys on the ground have to deal with the lower level. So this is how it works. So we talked about two ways of thinking about processes or plans or procedures. One is describe what is to be done. The second is describe what you want to achieve. And there's a third one which is very, very interesting, where you say, I'll describe neither of these things. I will not provide a procedure for you that you have to follow these steps. I won't even give you a sequence of goals or objectives to achieve. I won't do none of those things. I will simply write down some rules. Right? I'll give you a set of rules and I'll say, do anything as long as you don't violate these rules. That's what governments do. Governments do not give us a procedure for how to live our lives. Right? Governments say, live your lives as you feel free, as long as you don't violate the laws. Right? So what that is doing is that saying, okay, there is a big space of behaviors, the boundaries of which are determined by those rules. The rules determine the boundaries. As long as you're within the boundaries, you're okay. Any behavior is fine. You can have lots and lots of behaviors, and they're all okay. Just don't step outside these boundaries. So this is the business of specifying behavior by writing down rules. So this is very, very powerful. And what this is playing out nowadays in the business context is via a thing that we will talk about a bit more, hopefully with time, called adaptive case management, or ACM. So ACM is like business process management, but for knowledge intensive work. So they're saying, this kind of procedural description of processes does not work for knowledge workers. So if you're a surgeon, You don't want to, somebody saying, okay, now you cut this, now you stitch up that. You don't want that kind of detail, right? So you have other constraints that guide your behavior. So as a surgeon, you, for example, know that, no matter what, I can do lots of things. I am the boss, I am the star surgeon here. But there are some constraints I have to follow. So for example, I should not make an incision on the patient, immediately after the anesthesia has been administered, because the patient might still be feeling pain. So I should allow 10 minutes after anesthesia before I make the first cut. That's a rule. I have to follow the rule. So there are rules like that for me as a surgeon, but I can do whatever I like as long as I don't violate those rules. So this is the nature of knowledge work, where you're saying the rules constrain our behaviors, but they don't prescriptively specify the behavior. Right? There is no prescription that says first this, then that. You decide autonomously, using your best judgment, using your knowledge, using your understanding of the context, what the right thing to do is. So that's yet another way of thinking about processes or services. Right? So with business process models, what do we need? What kinds of things do we need to specify these? So it should be expressive, right? So this is very, very important. So expressive languages allow you to say more. We had a little example, right? With the furniture seller who only knew the concept of chair but didn't know the variations, the subcategories of chairs, right? So expressivity of your language is really important. You need to be able to say things. Your vocabulary must be wide enough, but other kinds of things, the ways in which you connect elements of your vocabulary also need to be very expressive. So it's very complex, and we don't even, I can't sit and say, okay, I've been working on this stuff for more than a decade, and I know all the kinds of enterprise functionality I want to represent in these notations, because I really don't. There are many things I have not even thought about that I might need to do, I might need to represent. So, but anyway, so we want to represent all enterprise functionalities to be really expressive, and then it must allow a whole bunch of different kinds of analysis. So you have the analysis for goal satisfaction. You look at a business process design and you ask the question, does it achieve the goal that by executing this process, I will be able to tell my clients if their insurance claim is accepted or rejected? Right? Does it achieve the goal? Compliance. The government has a rule which says that if you went to school with the person who's applying for the insurance claim, and you're the insurance claim adjuster, then you should not sit in judgment. And so you know this person too well, or if you're a relative or something. Conformance is this idea of, am I actually following the exact prescription given in the process model? Non-functional features, do you all know the idea of non-functional requirements? Functional versus non-functional requirements? I'm hearing a no, right? Is that a no? Is that a no or a yes? It's a yes. No. No, right? Okay, right. Good. So when you write down the requirements for any system, this is what happens in the requirements engineering phase of software development. You write two kinds of requirements for the system. You write the functional requirements for the system. So for example, I give you a programming assignment. I say, write for me a program which takes as input two numbers and produces as output the sum, the plus of those two numbers. Right? So now, what have I done? I've described the functional requirements for the system. This is the functionality it has to deliver. It has to take the two input numbers, it has to add them together and produce the sum as output. That's the functionality. Now you might write for me a program that does that, but it takes 10 days to produce an answer. It's an incredibly complicated program for adding two numbers, right? 10 days later I get the answer that 2 plus 3 equals 5. Not very good for me, right? So when I write down the requirements for this program that you have to write, I not only say that it must add two numbers, and by the way, it must do it in less than 1 second. Right? Now the fact that I specified this requirement that it must do it in less than 1 second is a non-functional requirement. It is not a statement of the functionality of the code, it is a statement of the performance of the system. So it must perform to this level. Right? So that's a non-functional requirement. So, yeah, so it's about efficiency, Or, if you are a software vendor and you're trying to sell me a system, I might say a non-functional requirement for me is that it must be platform independent. So right now I'm using these kinds of machines, but next year I'm going to migrate to some other platform. Your code must still run on that other platform. That's a non-functional requirement. It's not a statement of functionality, it's a statement of performance. Right? Or cost, write this code but keep it under 50,000 rupees. That's a cost requirement, it's a non-functional requirement. It's not a statement of functionality, it's a statement of the other aspects of the system. So everything outside functionality is a non-functional requirement. So you write these requirements, right? These often go into the software contract. Right? So the non-functional aspects of a business process can also be very important. So the boss says to the insurance company CEO says to the middle managers who are in charge of insurance claim handling, make sure that you design your insurance claim handling processes so that a claim can be handled in less than 15 minutes. Between the receiving of the claim and the decision on whether to accept or reject, it should be no more than 15 minutes. So your people say, oh, that's terrible, we used to take 10 days to decide, now you're saying 15 minutes. Okay, so you've been given a new non-functional requirement, right? So you want to be able to look at a process design and also say, okay, its non-functional properties are like this. It will take this long, it will cost this much, the quality of the product will be like this, etc., etc., all these other things. So this is also very important for processes. Let me skip the next one and talk about provisioning. So this is about, so if I give you a process design like this, right, so this process design says, first do task 1. Then, based on whether P is true or not P is true, you branch either on this branch or on this branch. And then these come together, and then you do task T4, and then you're finished. It's a process, right? Now, this is not saying everything that I need to know, right? So, for example, when I'm executing the process, if I'm the person that's in charge of executing the process, one of the first things I will turn around and ask the boss is, okay, so who does T1? What resource does T1? Or what set of resources do I use for executing T1? What resources do I use for executing T2? So this is the business of provisioning, right? So provisioning means providing resources for doing things. That's a very, very hard problem, and often people say that that is the key determinant for how successful a process is. So, earlier people used to say a process is really good if its design is very good, something like this. But then they found that even the best designed processes sometimes didn't do so well. And then they said, aha, we know why. Because the resources we are using are not so good. So if we give better resources, it will perform better. Then of course there's a third reason that has emerged now. People are saying even the best design with the best resources sometimes doesn't do well, and that's because of the context. So I have a really nicely designed insurance claim handling process. I have really good trained call center operators who are sitting on the phone handling calls from customers, but it's May in New Delhi and the temperature is 45 degrees Celsius and the air conditioning has switched off. Suddenly the process is not executing so well, right? So sometimes the determinant for how well the process executes is the context. In this case, the temperature in the room where the people who are executing the process are sitting in. Right? So all these things matter, which is very interesting. Okay, so tea time. Tea time. So I'm supposed to give you an exam on Saturday morning, right? Is that right? Are you all prepared? You know what question types you're getting? Professor Bhaskar, they're all taking an exam, right? They're taking an exam on Saturday morning.
Saturday morning?
Yes, there's an exam for this class, right? Yeah, so I was asking if they're all well prepared for the exam. They're not getting the humor in my question, but okay. Just one little detail. I think on the official program we have the exam starting at 10 o'clock. It's a 2-hour exam, so I'm not going to make life terribly difficult for you, just 2 hours. Instead of 10 o'clock, we'll start at 9 o'clock. So 9 o'clock to 11 o'clock, final exam. Not possible. Why not possible? You won't reach? Why not? People start their offices at 8 o'clock, right? So how come you can't reach at 9 o'clock? You see, it's the constraint is like this. I have to leave for the airport at 2 o'clock. And you will be writing hundreds of pages of answers, right? So thick pile of answer sheets. I can't possibly carry it into the plane with me and then mark it on the way back, right? So I have to mark it here before I go to the airport. And I need at least 2.5 hours to mark. Right? So at least from 11:30 I should start marking. So that I can finish my marking at 2 o'clock. I will give your professors here the marks and then I can take off, right? So, but the other thing is they need access to these notes. Is there a website we can set up or something where we can put these? Yeah? Okay. So I will starting from today I will start providing these. So who should I email it to? I should email it to somebody, right? To you? Okay, I'll do that. Okay, so resuming our lecture. So the last thing we were saying was what do we need from this, the notation in which I write my process models, right? So it should support all this kind of analysis, but it should also be at a level of abstraction where this business is comprehensible to human stakeholders, and that's very, very important. So in fact, the notation we are going to learn now, BPMN, had that as a very important design principle, that non-technical people should be able to look at a model and say, okay, I understand what's going on. Those flowchart-like notations are kind of like that, so you'd imagine that just boxes and arrows, how hard is it, right? So people should be able to look at it and say, okay, I understand what's happening. And as I also said, this notation, ideally it should be executable. So there's there's a large number of notations out there for writing down, for describing a process model. There are Petri nets, which were invented a long, long time back and have been around for a while. How many of you have heard of Petri nets? Anybody? No, okay. There is a version of the language we are going to learn now called EPC chains, event-driven process chains, which was the process modeling notation that SAP, I'm sure all of you know SAP, right? SAP. So SAP used that notation for all of its processes, right? So an enterprise resource planning software system, any enterprise system is ultimately a implementation of a large variety of process models, right? So SAP does that as well. So they're essentially saying for every kind of possible enterprise function that you might have, we have a process model ready for you. And so all these people that get paid a lot of money to customize an SAP implementation, what they're basically doing is and often they're domain experts, they're accounting experts and so on, right? So what they're doing is they're saying, okay, so there's a standard invoicing process that the software comes with. Now in my company, invoicing is done slightly differently. So I have to take the process that is described in the software, change it to fit what we do, and so on, right? So EPC chains was used by SAP. These days they have given up and they're moving to BPMN. There's a range of formal notations that are collectively called process calculi. So different kinds of process calculuses, if you will. So if time permits, I'll talk about them, but if time doesn't permit, I'll skip them. BPMN I will talk about now. So this is something that you can really get your hands on, and it's really important. And in fact, it's a very powerful, potent industry skill. So just a few years back, I had a first-year PhD student who had written 2 or 3 first-year papers on BPMN, process modeling, and so on. Then he applied for a job with the government in Australia. And he didn't expect he'd get the job, but then suddenly after the interview he called me and said, sir, they didn't give me that job, they made me the manager. So he had written 3-4 papers and he was like the most qualified person in the whole lot. So they didn't just give him that job he had applied for, they made him the manager of that team. So it's still very potent. I mean, there's lots of places where BPMN skills for business analysts is really important. So if nothing else, if you guys pick up this stuff and use it in your future careers, you might find, immediate career value from knowing notations like this. So BPMN. So the formal name is Business Process Model and Notation. So it's an OMG standard. OMG is the Object Management Group. This is the international standardization body for a lot of object technology, notations, and so on. It's intended to bridge the business IT divide. So the business IT divide is this idea that you'll find in a lot of places being talked about. This is the idea that in an organization, there are the people who handle the business end of the story, right? And then there are the people who do the IT. Take any organization, right? There's, I'm sure there's a pizza chain like this. Domino's Pizza here somewhere? Yeah, there is, right? So Domino's Pizza. They are the business end of the organization who make pizza, sell pizza, deliver pizza, and so on, right? And there are the IT in Domino's Pizza who will be building the IT system that supports all the promotions, campaigns, accounting, billing, etc., etc., right? Now the funny thing in all such organizations, it's a phenomenon that people have observed. It should not be that, but it's been observed that the IT people and the business people live in different worlds. They talk different languages and they look down on each other. The IT guys say, these guys don't know programming, they're useless to talk to. And the business guy says, they live in some la-la land where they're doing computers and stuff. We make the pizza. We know the real stuff, right? So there's this big divide. It's true in almost every organization. So the original intent when people designed this language was to also say that, okay, we want to bridge this divide. It should be equally accessible to the business guys and to the IT people. And it should be equally interesting to both. So it's an executable specification, which means that these BPMN models can be directly executed on process engines. So let's take that simple example we were using earlier, this one, right? So the intent is that something like this should be understandable to managers and be of interest to the IT people, and it should be executable. Now you'd look at this and say, okay, this is understandable to a manager, right? I mean, you don't need a PhD in computer science to understand. You receive some information, you send something, you open an account. These are concepts that managers can understand. And these are just boxes and arrows. There's not even maths here, right? So first you do this box, then arrow this box, and so on. But here's the funny story. So while this was how it was intended to be, it is now not how it pays out. So when you actually look at actual organizations where BPMN is being used, I have seen in my personal experience lots and lots of cases where people, managerial people, look at a model like this and say, no, please don't show me this stuff. I didn't do computer science in my undergraduate degree. No, I didn't do a PhD in computer science. I am an MBA, so please show me something that I can understand. Now that's very funny, right? Because you're saying, come on, anybody should understand this. You don't have to get a PhD in computer science to understand a notation like this, but this is the nature of the pushback from actual business people. So the managers and so on, they don't want to know this. So I had a bunch of my ex-students, they opened a consulting company which was consulting for various branches of the Australian federal government. And they were all, I had taught them BPMN and process management concepts. So they were going to use this in the various government agencies. But the thing that they would come back and tell me is that, we showed these senior managers the BPMN models, and they said exactly that we don't understand this stuff. So in the end, what they had to do? They had to make PowerPoint slides. And so in the PowerPoint slide, they would write those things in dot point form. First this, then this, right? And then those managers would say, aha, I understand, that's what you're doing. So you put this even in this form and they are scared, which is very funny, but it shouldn't be the case. But that was the intent, that you don't want to scare those guys. You want to have a language which is equally accessible to both parties, right? So back again to where we were. So executable specification, because the idea is that these models can be parked on these programs called process engines. They are coordination engines, right? And they can be executed. So I'll give you an example of what it means for a process engine to be a coordination engine. So remember I was saying a coordination engine doesn't do the doing. A coordination model doesn't do the doing. It merely coordinates the doing, right? So in many hospitals you have clinical processes, right? And the clinical processes are being executed by a series of screens appearing on the workstation of a nurse. So the clinical process says at 10 a.m. take the blood pressure of this patient. So on the nurse's workstation that shows up that okay, for this patient take the blood pressure. So nurse goes and takes the blood pressure, then comes back and enters it and so on. Then it says at 11 o'clock give this patient this pill. So nurse goes to the bedside of the patient, gives the pill, and comes back and checks a box saying okay, that's done. So you see this is a coordination engine. It's not checking the blood pressure. It's not giving the pill. It's coordinating the giving of the pill, the checking of the blood pressure. It's making the actual executors do the execution. It's just the coordinator. So that's a process engine. It coordinates but it doesn't do, right? So process engines can take a BPMN model and execute it, which is to say it will say the first task is check the blood pressure, so it will show on the nurse's screen now go check the blood pressure. Next task is give this pill, so it will show give this pill. But the doing is being done by the nurse, right? Okay, so now
It might be easy for the flow which you have shown the example, but if you have complex graphs, complex networks in the overall flow chart, some cases might be complex in such a way that like you may not represent in a simple mode. Then
of course. So there are actually devices for doing that. In fact, that is a very interesting and major problem in all of conceptual modeling. So for modeling of large software systems, I've heard war stories where people say we were doing UML modeling, which is standard for software modeling. So they said we had a hall, and we laid out our UML models on the floor, big sheets of paper, and filled out the floor space of the hall. And then to talk about what we had built, we walked over the models. We pointed out, okay, this is this, then we go there. So that's how complex things get. So people are spending time, in fact there are workshops and so on how to manage the complexity of large models. So you want to basically say, show me the parts that are interesting for me now, and then there must be some connection with the next part of the story. It is very good.
can a process engine actually handle this complexity? If we have
So yeah, general process engines can handle complex models. So there is no, there are probably obviously the kinds of limitations that come with the size of the RAM and so on. Otherwise, they can handle arbitrary complexity. There is a general principle that you don't. Which is you don't create very complex models. So one of the next things I'm going to say is that last point. It even allows hierarchic modeling. So hierarchic modeling is the idea that I do more layers of abstraction. So if I try to model everything at the lowest level of abstraction for any computational system, what will I have? All my tasks and activities will be reads and writes. Fundamentally, that's what computers do, right? They read and they write. So I'll have a whole complex, incredibly complex model that says, read this, write that, read this, write that. Not very interesting for organisms. What is interesting is the abstraction. At the level at which you say, check the credit history of the applicant. That's an interesting abstraction. It's not at the level of reads writes. There is a very complex story of reads writes lower down, which we don't want to know about at this point. So that's the other thing that is interesting is that this, so remember I was saying that this is about,
this is where computer science meets management, right? So BPMN is one example where there is some amount of that going on. So there are organizational structures, this is very much a management concept, that you can model inside BPMN in a very minimal fashion. So in BPMN there is this notion of a pool. So there's very much a swimming pool kind of a metaphor. So a pool is an organization. The boundaries of a pool describe the boundaries of an organization. And inside a pool you could have lanes. These are like departments or divisions in an organization. So I'll give you one example right here. where was our example? So here we have one single pool, but two lanes. So what are the two lanes? Two divisions, customer care division and the back office division, right? Two divisions within the organization. And so what by doing this, you're saying, okay, some activities are done by the customer care people, some activities are being done by the back office people, right? So you know who's doing what. So it's a kind of role modeling. So you are not only able to say, okay, what's the next thing to do, you also get an answer to the question, who does the next thing? That role does the next thing. And remember, this is role modeling. This is not actually saying who is doing it, right? I'm not naming the guy who's doing it. I'm simply saying that role does it. That role might be occupied by a certain person on a certain day, a different person on a different day, right? So roles are separate. In fact, and I'm not going to talk a lot about role modeling, but it's interesting for you all to know that role modeling is a really interesting, business activity in its own right. In fact, there are consulting companies who offer the service of designing role models for projects. So you'll start a new project. It could be a software project. It could be a project to build a massive bridge over the Mandovi River or something, right? So whatever the project is, you're sitting and saying, okay, I have a big project. What do I need? Do I need like one general manager, 2 senior managers, 5 junior managers, 20 superintendents? What do I need? What roles do I need? So these consulting organizations will come and tell you, okay, we'll tell you exactly what role you need. They will draw a hierarchy for you. You'll need this, you'll need that, and so on. So the business of designing a role model is a hard, knowledge-intensive task in its own right, and people do it. For the project. For the project. So as long, so in this example, right? So I'm doing this project. I need a role structure, a role model for this project. Give me one. I use it for the lifetime of the project, then I shut it down. Right? So. Because again, the complexity of the project and the specific demands of the project will require different roles, right? So for example, if there is a project that requires constant interaction with the government to ensure that government laws are being met or reporting is being done, I'll probably design a separate role who is the government liaison, right? But if it's a private sector project, then I will not have a government liaison role, right? So the role model is very much customized to the needs of the particular project. So it's interesting that you have, so you can do some role modeling by doing these swim lanes. And here's an example of pools. So that is a separate pool, and this is a separate pool. So what does this pool say? This pool is company, and that pool is candidate. So candidate is probably applying for a job, I think, with this company. So why do I have them as two separate pools? I'm basically saying that the two pools are two autonomous, independent organizations. And that has a very real computational interpretation. That means that control flow can only proceed inside a pool. So I can demand, manage, direct people to do things inside an organization. If you're sitting in one organization, you cannot demand or direct people to do things who are in another organization. So your interaction with other organizations is via message flows. So you can request, please send me, 10 packets of pizza. It's a request. And if they want to fulfill your request, they send you the pizza. But if they don't, they won't. There is no control that do it for me. Whereas inside Domino's Pizza, there is a ability to actually direct. Now you put the pizza in the oven, right? It's direction, it's control. So you have control inside the boundaries of an organization, but control doesn't span the boundaries of an organization. And that BPMN manages very carefully. They say that control flow links only inside a pool. Between pools, you can never have control flow links, you only have messages going back and forth. So between organizations, what you get is request response kind of interaction. I request you to do something, and you respond by saying, okay, I'll do it for you. So you call up the phone and request the pizza company to send you pizza, and they say, okay, we'll send it to you. But they're under no obligation, right? So we have this organizational modeling business going on in BPMN as well, which is very interesting, right? So So you have pools and you have swim lanes. And then it's hierarchical. So there is this idea that you can take a task or activity, one of those boxes, and you can think of it as an abstraction of a deeper underlying process. So you can click on one of those things and what you get is another process model inside it. So you can have a whole tree of processes, right? So a task becomes another sub-process. Inside the sub-process there is another task which becomes another sub-process and so on. So you can do complex hierarchical modeling in that fashion. And that's really important because for many processes, if you try to model the whole thing in one process, it will be impossible to handle. In fact, we've had a lot of discussions in my lab about what is the right size for human cognition, for a human being to understand a process model, what is the upper limit and the complexity of the process. We used a very simple measure. I mean, again, this is not carefully done research, it is just sort of experience-based insight. We said that, if a process has about 25, 30 tasks, that's max. That's how much a person can understand. You give a person 100 tasks in a process and say, okay, now read this and understand it, they can't. So 25, 30 is about max. Right? So this is a very common insight about the limits of human cognition. So the idea is that you keep the models simple, but you make them hierarchical. And then that's one way of managing the complexity. So it does that as well. So what are the elements in a BPMN model? So you have these 4 kinds of things: flow objects, connecting objects, swim lanes and pools, and artifacts. Now, as an aside, when I teach a class like this, there are things that are very conceptual about which I can't give you an exam question. And then there are things like this which are pretty concrete, hands-on. And about this I can give you an exam question. So I will give you an exam question where I will ask you to draw a BPMN model. So there's one question ready for you, right? Okay, so flow objects, what do we have? 3 kinds of flow objects: events, activities, and gateways. So an event is exogenous, which means its genesis, its creation is external. It happens in the outside world. So the process must react to it. Activities are endogenous, so it's being done by the process. And gateways are points where some decision logic is applied to decide, do I go this way or do I go that way? Right? So these are the decision points in some sense. So those are the flow objects. Then you have connecting objects. Sequence flow, which is like a command and control link which says, after I've done this, you must do this. Message flows, those request response kinds of things. And an association link, which we'll see later, it's not very important. Swim lanes and pools we talked about for describing organizational structure, and then we'll see these things called artifacts. So, activities, right? So it's a named procedure or sub-process or action, right? So this guy here, that's an atomic task, right? So by writing one of these things, I'm saying as far as this process model is concerned, this is the smallest unit of analysis, a task, right? So here's a task: send payment problem, cancel order. These are all tasks. Right? Now at the level of this process model, I don't want to go any deeper. It's atomic for me. That looks like a task, except it's got that little plus inside it. So the idea is that if you're actually in a process modeling tool and you click that plus, it expands into another process model. So this is your hierarchical modeling. Some tasks are sub-processes, they expand into another lower level process. And these guys are looped tasks, so they're sort of iteration. So not that commonly used. And then you have these decision logic, right, the gateways. So again, this is basic flow charting, but it's very interesting when you look at it in detail. There's some amazing detail and some amazing complexity. And we'll see that over today and tomorrow, tomorrow as well. So this is an XOR gateway. XOR, right? So XOR, if you think about logic, XOR is exclusive OR, which means that I do this task, then I come to this gateway, and let's say this is an insurance claim handling process. I make a decision here. I will accept. If I accept, I go along this path. If I say I will reject, I'll go along this path, right? So it's a simple decision being made based on acceptance or rejection of an insurance claim. And this is where they come together. So this guy is an XOR split. It splits the flow. and this is where it joins, so they all come together again. So for every split, there must be a join. For every, so because you're basically saying that, I'm splitting into multiple flows, but it must come together again. So that's a join, right? So this was one little example where we had a XOR split and we had a join. The splitting, the decision condition here was P versus not P. So if P is true, I go on the upper path. If not P is true, I go on the lower path. And ignore the ESs for now. We'll talk about those guys later on. So that's a gateway. So there's an alternative representation for a gateway. So the first representation had an X inside this box, inside the diamond, right? So now here we're saying if I don't write an X, it's also an XOR. And this little line across this flow, this sequence flow link, says that this is the default. So if by default I will go on this path. However, if the payment is not okay, I will go on this path. And if the retry limit, you're allowed to retry 5 times, let's say, has been exceeded, I will go on this path. By default, I'll go on this path. Right? So it's a simple logic there. Yeah, so it's some extra syntactic sugar really, because logically speaking, the condition says it all. Right? You can't have 2 conditions that are identical and you say this one's default. That makes no sense at all. Right? So basically, you're saying that I have 3 distinct conditions. Whenever any one of those conditions is satisfied, I'll go on that path, and it's mutually exclusive. It's XOR, which means that I cannot have more than one condition satisfied at the same time. There's a guarantee by design that must be the case. So now we have AND gateways. These are very interesting. So an AND gateway, so I do this task, right? I come to this gateway where there is a plus inside it. So what I'm saying is now, I will split into 3 flows concurrently. In XOR, I only pick one, right? Here I will go on all 3. I'll go on all 3, and I will do stuff, and eventually they'll come together in an AND join, right? So what's happening here? What I'm really saying is that these are parallel flows. So this flow can be done in parallel with this flow, which can be done in parallel with this flow. Right? Which is interesting because it's not actually saying that, it must be truly concurrent in the sense that is used in computer science, which is that, it's happening at exactly the same time. There is no requirement for that. It simply says that this guy can be done before this guy or after this guy. We don't care. They are on parallel branches. I can mix them up any which way I like. I must maintain the sequencing relationship here. I must maintain the sequencing relationship here. But between these guys, I have no sequencing constraints. I can do whichever one first or later or concurrently. I don't particularly care. Right? So what is an AND useful for? That's a very interesting debate I often have with my students. So one of the propositions I put to my students is that, for describing functionality, you don't really need an AND. For describing functionality, you don't need to specify things that must be done in parallel. So you could do away with the AND. So the only value for AND is for improving the efficiency. So you can say, in an insurance claim handling process, I have to do a check of the validity of the customer's address, and I have to do a bank history check, for example. So there is no dependency between these 2 tasks. There's nothing that says I must do that first and this later. I can do them in any which way I like. So I can put them on 2 parallel paths and say, okay, even as you're doing the bank history check, you're also checking the address validity of the customer, right?
But the process will not go in front of the end until all the processes are complete.
So you cannot go past this point until all 3 flows coming in are complete. That is definitely the case. In fact, we'll look at that kind of constraint in more detail shortly. Right? It's funny because, as I said, even flowcharts have deep mysteries inside them, and so there are some mysteries here. So that's an AND gateway. Now, the debate with my students, right? So I said, so you don't need, you can describe all possible functions with just XOR. You don't even need an AND. So they said, no, sir, how about, in a gear shift car? So in a gear shift car, just sequentially relating the pressing of the clutch. How many of you drive cars? Some of you, makes sense to some of you, right? Most of you have seen a gear shift car being driven. You press the clutch and then you shift the gear, right? So now they're saying, okay, these two must happen in parallel, right? So clutch pressed and in parallel gear is shifted, right? So then I need an and to describe this. So I argued against that point. I said, well, I could describe it like this. I could say first perform the action of pressing the clutch. And that action means basically the clutch is pressed until further advice. So clutch is pressed, right? You're not unpressing it. And next, shift the gear. Now I have a sequential description of what you were saying was a parallel description. I was given another example. I said, suppose I'm lifting a heavy table. I need two people to lift the table. So I lift one side, you lift the other side. So again, do I need to do it as a and? So I'm saying both these things are happening parallelly. One person lifts one side, other person lifts the other side. Again, you can do the same kind of solution that I suggested. So it's very interesting. Ands maybe are not fundamental to describing functionality, but they are pretty useful because you can talk about things that can be done in parallel, and thus often one simple way of doing business process optimization is to take sequential activities and make them parallel. The act of doing that makes things faster.
Parallel tasks makes much more sense for managers because they think, okay, I can do these in a parallel way and make things faster. But if the sequence way, okay, I went through these first and then I go here.
Correct. So in fact, the idea then is that sometimes it might be the same person who's doing all three flows, all the three parallel flows. So then what you're saying is that I don't particularly care in which order you do them. Just do them. And then that gives the opportunity for the person to say, okay, I had to wait for the bank history check result to come back. I don't need to finish that task before I start the next one. So I can do the other one in parallel as well, right? So this is the optimization that you can do. So those are AND gateways. There is another thing called a OR gateway. So this is different from an exclusive OR, where exclusive OR means only one branch can be selected. This OR is inclusive OR, which means all the branches can be selected. So it could be only one, it could be two, it could be three, it could be all. So it's a mix of XOR and AND, right? So that's an OR gateway, but I won't spend much time on it. People don't like it. People often try to avoid it. It's very messy. So it's really at the canonical level, there's two really important gateways, AND and XOR. Right? So we've got our gateways right. Now we have the events. So three kinds of events: start events, intermediate events, and end events. They are written differently: single line, double line, bold, thick line. So start events are the events which start a process. They are the triggers for a process to start. Intermediate events happen in the middle of a process, and the end events at the end of a process. So we've got a bunch of, let's see if there are events here. So yeah, there's a start event, there is an end event. There's not much else. There is a AND gateway, there is an XOR gateway, and there is an inclusive OR gateway, all inside the same process. We have only one pool. We have 3 lanes inside that pool. So basically 3 departments or divisions inside the organization. What is this organization? It's a hardware retailer, and they have a warehouse worker, a clerk, and a logistics manager. Right? So 3 different roles inside the one organization. Okay, start events. There are many kinds actually. I mean, I've only picked the ones that are interesting. This is, there's nothing specified. It's just start when you start. This is where you're saying start when you receive a message. So for example, a warehouse process starts when you receive an order. A timer says you start this on every Friday morning, for example. A conditional event says every time a rule is fired, start the process. So different conditions under which you start a process. So here's one example. So this is a message event. So the arrival of the message triggers the start of the process. So the message is a credit request. So now the first task you do is evaluate credit report. Next task you do is approve credit. Then you check, is the credit approved? If yes, you do some stuff. If no, you do some other stuff. Right? So it's a start event. By the way, just looking at this, can you criticize BPMN for something? Just looking at this part of the story. There's something interesting going on here. So BPMN will only allow you to write a relationship between two tasks of the following kind. The relationship is that when the first task ends, then the second task starts. So you can only constrain these things to say the end of one precedes the start of another. What if I wanted to say the start of this task must precede the start of this task? Can I write that in BPMN? You can't. What if I wanted to say the end of this task must happen after the end of this task? Can I say that in BPMN? I can't. So the only constraints I can write in terms of sequencing are end, start constraints. I cannot write start constraints. I cannot write end constraints. That's very interesting because that limits, again, remember what I was saying, that the language limits what you can do? This language limits what we can do. I cannot talk about those kinds of process designs where after I've started the one thing, I must start the other thing. I don't care about the ending, right? I can't write those constraints. I cannot write those kinds of process models. The language does not permit it. So you can see the expressivity of the language has a lot to do, yeah? Tell me how. That'll be very interesting. Think. Use the whiteboard. Show us. That's what it's there for. Come on. Just call it task 1 and task 2, T1, T2.
We can use a AND gateway, but then start. It will just like.
So this event will start right after this.
They won't start at the same time.
Yeah, but suppose I wanted to say, I want to do, let's say that's this one, let's call it task 1, and this is task 2. Suppose I wanted to say that the only thing I care about is that task 1 must start before task 2. Does that say that? See? So I've thought about it and I can't find any way in which you can say that.
So if you want to say that we must include something called timeline.
You must introduce other stuff. You must expand the language because the language as it stands now does not allow you to say it. Similarly, end. Suppose I want to say task 1 must end before task 2 ends. Right? So actually it's happening here, by the way. It's happening here, right? Is it happening here? So it is true that task 1 ends before task 2 ends.
Task 1 is ending before task 2.
True, right? It's happening here. It's also true the first one. Task 1 is starting before task 2 starts. But what's not happening? Think about what's not happening.
So we have this happened. This is what is each like. But we don't have this is the relation of the.
So this is interesting. Why? Because I might have opportunities for speeding things up, right? Squishing things into a shorter duration of time by doing that second thing. But the language doesn't let me, right? So we're stuck. Okay. Here's another example of a start event. So this is a timer event, right? Start every Friday. This is a rule-based trigger. So it says if the stock price drops below 15% of the purchase price, then get rid of the stock, right? So when the rule triggers, then I do the process for selling the stock. So these are different kinds of start events. Then there are intermediate events. So intermediate events, there's again a whole bunch of them. I've just shown a few. There's two kinds. You can think of them as catching events and throwing events. So catching events are where you're responding to something that's happened. And throwing events is where you trigger something, right? So one's a response, the other is a trigger. So the first one is a none, right? So this is nothing. Timer. So it's a response. So when the clock strikes 12, right, then something happens. It's an intermediate. So it sits in the middle of a process. This is when a message is received, then you do something. But if it's a throwing one, then you say at this point you send a message. You're not waiting for the receipt of a message, you send a message. It's also, you can do this with signals. Receiving a signal, sending a signal. So here are some intermediate events. So validate order, then you receive an event, say, well, it's an internal event that says, that simply signals the fact that the order has been validated, then you do this other stuff. Here you announce issues for discussion, wait for 6 days, then send another email. Right? So it's particularly useful for doing these timing breaks, right? So one of the examples I give my classes to model is, library book return. So you're late, so you send a notice saying, okay, your book is late, you have 7 days to return it, before which we'll charge you a fine. Then you wait for 7 days. So you use this device to wait for 7 days, right? Throwing. So throwing, it's very simple actually. So you decide that something is rejected, then you send a message or you send a signal. Yeah, I don't have an example here, but I'm sure we can dig up some. Right? So look up BPMN models on the web. There's thousands of them. Right? So there are lots of examples.
So in the next testing intermediate events, say you're giving an intermediate of wait for 6 days or something. But can we write some trigger that if you get this trigger, then stop waiting and continue with something else?
That's interesting, right? Yeah. I've had one other person ask a similar question before. I don't think there's anything easy that you can do. That's very hard to do. Again, it's a limitation of the language, right? The language limits what you can do. So that's good because you can think of lots of these kinds of things. So, and if nothing else, you take away this lesson that somebody teaches you a new language, a new notation. The first thing you do is you sit there and you say, why is it like this? What can you not do? Criticize the hell out of it. When I was in primary school, when I was in class 4 or something, I was being taught physics, right? So they said speed. Speed is distance over time. You know what I asked my science teacher? Why is it not time over distance? Speed. And I have never gotten a real good answer. Can anybody give me a good answer? Why speed is not time over distance? Really, I mean, if I am a school kid and I say, I'm faster than you, then my friend and I, we say, okay, we're going to run from here to there, and we will see who gets there faster, right? That's speed. Then it's time per unit distance is what we're measuring. That's more intuitive. So why do we do it the other way? Distance over time.
Because we use this speed usually for predictive modeling, not for measuring something. We predict, right?
No. Speed is used for description as much as for prediction. Come on. It's not just prediction alone. And even the fact that you are trying to predict doesn't mean that, time over distance doesn't make sense. So does time over distance invert? The point of my example is that, sometimes the act of questioning what you're being taught is very, very interesting. It gives you very interesting.
Actually, Google Fit uses that metric.
What?
Google Fit, it uses the
time over distance, right?
It doesn't matter, right? It is just a convention which you are following. If you are considering time over distance, it will be an inverse relation.
So what's acceleration then?
Time squared by distance.
It's a bit complicated when you go to second order derivatives, right? I know. I mean, my first thought was maybe it doesn't matter. It's just inverting the one thing to get the other. But maybe it does matter. Anyway. So, intermediate ones we've done. End events. At the end of a process, either you just say, okay, this process finishes. Nothing. Or the process finishes and sends a message saying that I have finished, or it finishes and sends a signal of some kind saying that I have finished, right? There are some others, so simple enough. So now there's something interesting that you can ask. So again, we're in the business of criticizing, right? So criticizing this idea of events. So an event is a condition of interest that becomes true in the context in which the process is happening, right? So that's really what an event is. But, and so everything that we have seen so far, all these event types, they can all be described as some condition. The clock hit 12 o'clock, the day was Friday, a message was received. These are all conditions in the context of the process. But BPMN only allows you to talk about some conditions, but not all conditions. So it's again a limitation, right? Ideally, I would like to have all conditions. I might like a version of BPMN where I say, I don't make a difference between a timer or a message or a signal or something. I simply will refer to some condition and say, okay, if this condition becomes true in my environment, then this is an event I want to worry about, right? It's an event I want to recognize, and it's an event I want to respond to. So this is reactive processes, right? So a lot of processes are not reactive. Right? So I'm a travel agent and you come to me and say, I want to book a holiday in Kashmir. And so I say, okay, sir, I have 5 good 5-star hotels for you. I'm not reacting to the fact that you're a student, you're a budget traveler. You don't want to hear about 5-star hotels. You want some good youth hostels, right? So I just follow my prescription, my procedure and say, okay, here is the Taj, here is the Oberoi, here's the that. And you're saying, this is a stupid travel agent. What's he giving me this stuff for, right? I want youth hostels. So reactivity, the ability to respond to what you sense in the environment is important. And a lot of times, things that you model in BPMN does not allow you to do that. So that's interesting to keep in mind. Right? In fact, people are beginning to worry about how to do things with settings where BPMN falls short. So there's one simple thing you could do, for example. You could ask with a XOR gateway, right? So I decide that the payment was not okay. So I went on this branch, right? And about 2 minutes later, I suddenly realized that that decision I made that the payment was not okay was based on an error in the data. In fact, it is okay. Okay, we're back. All right, so I think it's still a good time to end. Hard question time. Hard questions? You get an extra.
I understand it's like evolving trying to take the complex cases or the piece right now just
A little bit, not much. Where it is evolving is in a different direction. So remember I was saying that one of the things that you would do if you're trying to model knowledge work, right? The process is followed by a lawyer or a surgeon, right? You don't use a process model like that because they don't follow some kind of a prescriptive procedure like that. Instead, what you do is you constrain what they do with some rules. You say, satisfy these rules and then do whatever you like. So this is called case management. And so now OMG, the same guys who standardize all of these different notations, UML and so on and so forth, who standardize BPMN, they have a standard called CMMN, which is case management model and notation. So this is a notation in which you specify case management problems where you describe allowed behaviors by essentially writing down rules. So that is happening. And there is another thing that is happening, and these are both things on my agenda. If I am able to make progress and if you're all very excited, you show that you're excited about what you're learning, then I'll teach you this stuff as well. Something called DMN. So this is decision model and notation. So now they're saying that instead of, so a big part of what happens in a business process is that a sequence of decisions are made. So the idea is, can I focus on just the decisions? So the decision modeling notation does that. It just focuses on the sequence of decisions being made and the decision logic and ignores the other actions. So it basically says, first I decide this, then I decide that. And arguably that's really what's happening, right? I mean, if you think about the if a human's activities, behavior, it's really a sequence of decisions, right? I decide to say something to you. Then I decide to switch off my laptop, right? So these are all a series of decisions. So that notation focuses on the decision modeling as opposed to the modeling of activities. There is that as well. So these are two new things, very, very new things that are coming up. which might be interesting. So curiously, CMMN has not taken off very much. So some companies have built tools around this standard. They're trying to sell it. Not taken off so far, but maybe it will. Maybe it will.
So some good BPMN, whether it is.
BPMN is big. It's massive. BPMN is absolutely massive. It is used everywhere. Every enterprise software system is essentially, as I said, a collection of implemented process models, and you can look at inspect the process models, right? So this is true for all ERP systems and most enterprise systems. Yeah, so business analysts are the ones who do the designing of the processes, but in a ERP system, for example, the ones who are involved in the customization of the ERP system for a particular organization will take the process design and say, okay, for us, this one's different. So they tweak the edges of the processes, right? This is also heavily used in a lot of very, technology savvy organizations.
When they worry about what is the process, I need to model our processes, I need to understand what they're like before we do anything with them.
So what about some extensions, like for example, here we saw the AND gateways, right? So something very simple like timeline can easily be accommodated in the language. So are there any extended versions of BPMN which involves...
What can be accommodated in language, you said?
An extended language, like extended feature like timeline can easily be accommodated in the BPMN, but is there...
So there is nothing that is going on as far as I know that is going to extend BPMN in those directions. It's not there right now. But yeah, I mean the whole point is, so there is a lot of activity now in the area of knowledge-driven business process management. So we're just in the process of finalizing a special issue of the ACM transactions on IT on knowledge-driven business processes. So a lot of interesting stuff's happening right now. One of the things IBM is now promoting is something called cognitive BPM. So, the idea that Watson, so when IBM says cognitive, it means Watson being used for something, right? So Watson being leveraged for BPM. So they're very interesting ideas. They're saying, maybe we don't need process models. Maybe if you make your Dropbox files or your Google Drive available to me, I will look at your emails, I will look at your email, I'll look at your Google Calendar, I'll look at any documents you have on the drive, and I will compose dynamically the process you need to follow. So there is no process modeling. Right? Or I will learn dynamically how to adapt. So with some of my colleagues, we've written a paper recently on using Watson to do data-driven adaptation of processes. So all that stuff's happening.
What we spoke yesterday at class, Watson is a black box, right?
Many black boxes actually. So not one.
In Atlas, it's a neural network.
No, that's one of many things that it uses. Other questions? I'm especially interested in hard questions. So whenever I ask my classes what is a hard question they can ask, somebody always says, what is the meaning of life? And then there is an answer to that question. You know what that is? The meaning of life is 43. 42. Was it 42? I was one off on the meaning of life. So anyway, there are hard questions and there are hard questions. No other questions for today? Okay, thank you. See you all tomorrow.